TAO is a fundamental physics experiment. It's an atomic physics experiment. We're going to build or develop a system which allows us to create a ultra-cold quantum gas on orbit. And we're going to be able to take this gas down to temperatures that are so low that we actually see something called a Bose-Einstein condensate. And that Bose-Einstein condensate is at a temperature of around 100 picokelvins. It's 100 times 10 to the minus 12 Kelvin. And at those temperatures, matter actually behaves entirely differently. At room temperature, matter behaves like particles, like billiard balls, knocking into each other. But at temperatures below the Bose-Einstein condensate temperature, matter actually behaves as something called a matter wave. And at the temperatures that we're going to see on the International Space Station, we're going to see macroscopic matter waves, which is kind of a new phenomenon which is enabled by going to ISS.
So how does this instrument work?
So the instrument works by a process called laser cooling. So it's a little bit counterintuitive where you fire lasers or something that you actually can cool it down. But it actually works that way because lasers are made up of particles of light, or called photons, and those photons actually have a momentum associated with them. And so you can actually push on particles with photon momentum to slow them down. And so we have two stages of this laser cooling phenomena. And then finally we have this RF cooling phenomena where we get it down to an even colder temperature. So it uses an optical system, a laser system, and an RF system to be able to get down to these incredibly cold temperatures.
When you take atoms and you cool them down to a very low temperature, you can actually work with their quantum wave function instead of the classical particle of each atom. And by sending them on two different paths at the same time, quantum mechanically that's possible, I can make very precise measurements of accelerations due to gravity, of interactions with particles that we may know about and we don't want to see, or particles that we don't know about and do want to see.
We study it to understand the fundamental physics of the universe. So people potentially believe that at the beginning of time the universe could have been formed by these ultra-cold quantum gases. So we're going to understand more about how matter behaves at these temperatures. So there's a difference between Newtonian physics and quantum physics, and so it's kind of the same thing. There's a difference between matter at room temperature and matter at these ultra-cold temperatures. There are potential technology follow-on applications as well, but the purpose of our experiment is to understand the fundamental physics of what's going on at these incredibly cold temperatures and how these macroscopic matter waves actually interact with each other.
We know that our theories of gravity and our theory of particle physics don't get along at high energies. Everything works fine at low energies, but it doesn't work at high energies. This is a known problem and is a big problem, the biggest problem that we have in physics. And so we're hoping to get a hint as to what's happening at higher energies by looking for small deviations from the laws of physics as we think we understand them now at low energies. And so looking for gravity to tug on one kind of atom differently than it tugs on another kind of atom is a great way to probe this kind of physics. Well, the ISS gives us a microgravity platform which allows us to test gravity in ways that are very hard to do and more or less impossible on the ground. On the ground, gravity is very strong. It accelerates your atoms very fast. You have only a fraction of a second before they hit the wall of your vacuum chamber. On the ISS, you can hold the atoms and run the interferometer for seconds, tens of seconds, and get a much more sensitive measurement. It also is a nice environment where we can cancel systematic errors. Here I need to subtract the known acceleration of gravity from the Earth and get a small signal from it. On the ISS, the small signal is most of our signal. Plus we can turn the experiment around, put the Earth on the other side of the experiment. And so any systematic error that gives us a signal in one direction relative to our apparatus will rotate with our experiment, but the signal from gravity does not, and so we can actually subtract that out better.
We're delving into a temperature range that we've never seen before, so we actually don't know what we're going to see. So it's kind of the reason why you do scientific exploration is for discovery, and so by definition what we're doing is discovering a new physics as a result of this. It also enables us to use our expertise at JPL to create a system which ordinarily a mission like this would be a lot more expensive, but because we can put it on the International Space Station, because we're able to put it in a shirt sleeves environment, we can do amazing science for a really reasonable cost.